Let's say I place an ice cube on my hand. Why would I do that? I do not know. Maybe I just want to show how tough I am. So anyway, we have this scenario and I want to calculate the entropy for this scenario. So I'm going to define the system. I'm going to say that the system in this case is the ice cube. That is not how you spell ice. And that the surroundings are defined by my hand. So what is the entropy of the system? So delta S system equals the heat of the process, and we are assuming that it is a reversible process, over the temperature at which that process takes place. So what is the heat of the process in this particular case? Well, the process is the melting of ice. So we need to look at the heat of melting of ice, which is also known as the heat of fusion, or delta H fusion. And what is the temperature? Well, ice melts at 0 degrees Celsius, which is 273 Kelvin. So that is the temperature of this ice cube here, 273. And what is the heat of fusion? Well, we can look that up. And it is 6.01 times 10 to the power of 3 joules per mole. And let's say that there are 2 moles of ice, just to make it a little bit interesting. So all of that over 273 Kelvin. And we should get 6.01 times 2 is 12.02 times 10 to the power of 3 joules. The moles cancel. Over 273 Kelvin. And that should be 44 joules per Kelvin. So that is the entropy change for our system. Now let's look at what has happened to the surroundings. So the entropy change for surroundings, which I have defined as my hand, equals, we can use the same equation, so the heat of the process over the temperature of the process. So what is the process? Well, the process is the melting of the ice. It's delta H fusion. However, we have to be a little bit careful, and I'm going to write it down here beneath the hand. Recall that the heat of the system is equal in magnitude, so in size, to the heat of the surroundings. However, the sign changes. In other words, any heat that is gained by this ice cube during its melting equals to the heat lost by my hand. In other words, my hand is supplying the heat needed to melt the ice cube. That means that over here, I need to use a negative sign. I need to reverse the signs. Here it was positive, now it is negative. So negative 6.01 times 10 to the power of 3 joules per mole. And I'm still dealing with 2 moles of ice. So I need to multiply by 2. And I need to divide that by the temperature. Here you have to be careful again. You might be tempted to put in 273 Kelvin. However, that is the temperature of the ice cube. Now we need the temperature of my hand. And that is 37 degrees Celsius or 310 Kelvin. So we plug in 310 Kelvin. And we calculate that out. So now we have minus 12.02 times 10 to the power of 3 joules, because the moles will cancel, over 310 Kelvin. And if we calculate that out, we get negative 38.8 joules per Kelvin. So the entropy of the surroundings is not the same as the entropy of the system. So the system is 44 joules per Kelvin, surroundings is negative 38.8 joules per Kelvin. So what is the total entropy? So we can say S total, which can also be written as the entropy of the universe, equals the sum of the entropy of the system and the change in entropy of the surroundings. In our case, that is 44 joules per Kelvin plus negative 38.8 joules per Kelvin. And I'm going to rewrite that just to make it a little bit neater. So 44 joules per Kelvin minus 38.8 joules per Kelvin, which is 5.2 joules per Kelvin. So the entropy of the universe has increased. And this is true of all irreversible processes. So let me write that down. So irreversible process which is the entropy change in universe equals entropy change of the system plus entropy change of the surroundings is greater than 0. So for any irreversible process, the entropy change for the universe will be greater than 0. And that is essentially the second law of thermodynamics. Now, I should mention one more thing here. Remember that in real terms, every process that we see around ourselves is actually irreversible. But even if we could have a reversible process, even if we could have a reversible process, so let me write that down, a reversible process, what would that mean? That would mean that there is no change in entropy. So the overall entropy of the universe would have to be equal to 0. Or the sum of the entropy of the system and the change in entropy for the surroundings would have to be equal to 0. So the best we can hope for, the ideal situation, is that the overall entropy of the universe would not increase. But the overall entropy of the universe is constantly increasing. And that is the second law of thermodynamics.